Hello.
Hi. What's up?
Well, it's a snow day at the Generoo house, and so I thought I'd send you this video lecture from my house. And my kids are home from school today, so they thought they'd sit in and learn about electricity today. So, this is Emily, this is Thomas, these are my kids, and they're both very interested in science and technology, aren't you kids?
Yeah, I am anyway.
Really like computers, and so they don't know anything about electricity as far as I know. I haven't taught them. I don't think I've ever taught you kids anything about electricity, have I?
No, we go to school.
Yeah, so anyway, so they're home today, and I'm making them go to school. How about that? All right, so today we're going to talk about electricity and everything you ever wanted to know and more. Before I forget, I wanted to note that today is number 3, Electricity Basics on the wiki. The note takers for today are Jordan Wamser and Tony Tadigan, and if you guys would be sure to get in there and make some notes on Electricity Basics, that'd be great. And as always, anyone is free to get on here and add anything that you wish. What is electricity? Did you guys know that lightning's electricity?
Yeah.
Okay, you knew that. Where else do we see electricity?
In generators.
Oh, wow. You know that word generator, huh? Okay, we'll get to
that. Coal.
So light bulbs. Yeah, we use electricity all around the house. We're dependent on it, right? So, for most people, a lot of people, electricity just comes from the hole in the wall, right? You plug it in and you got it. They don't really think about where it comes from or what it's made of.
It comes from coal.
Maybe I have talked to you a little bit about electricity in the past. Okay, so let's talk about atoms a little bit. Okay.
I know one.
You guys know what atoms are?
Yeah. Everything's made of atoms.
Everything is made up of atoms. Very good.
Oh my gosh.
Okay. And
Big Bang Theory.
It's what?
From the Big Bang Theory.
Yeah, the Big Bang Theory shows an atom like that. That's right. And in the outside part of the atom is made up of protons, neutrons.
There's like
in the middle of the atom is protons and neutrons, and in the outside of it are these little tiny particles called electrons.
Okay, so it's like a whole bunch of circles surrounding. One big circle and a dozen smaller circles circling around it.
Something like that. It depends on what the atom's made up of, but that's the basic idea. But when these electrons jump from one atom to the next, when they move, that's electricity. So I want you all to feel the power of the atom. I got a little movie here that shows the power of the atom.
Feel the
5, 4, 3, 2, 1, fire.
That's the test of an atom bomb. Back in the 50s they did that.
Yeah, that's a pretty big bomb.
So anyway, what happened there is they would split the atom and make an explosion when those atoms are split.
Oh, I thought you said when two atoms bang together. That's right.
When two atoms bang together, that was how they split it. That they made the bomb. But anyway, we're getting off topic here. That's a whole different use of atoms. But electricity is where the atoms jump from the electrons jump from one atom to the other. Okay. Oh. Electricity is the electrical charge. It's a flow of electrons. Just like I said, they move from one atom to the other. And, okay, let's stop with... Unless it has to do with electricity, no more drawings, okay? Alright, so up here we see a slide here. These are conductors. Alright, conductors are a Conductors are a special kind of atom, okay? Here, you were asking about the circles around the atoms, Thomas?
Yeah.
All right, so check this out here. Whoop. Let's go back. Previous. All right. So look at these atoms here. Okay? These are drawings. They're inside. There's the nucleus, and all these little dots around the outside are the what's the particle called?
The neutrons.
No, that's in the middle. What's the ones on the outside?
Electrons.
Electrons, right.
Like
Electricity is made of electrons.
Like
Well,
one.
check it out. These are called shells here, okay? And
Shell.
when the shell is full of electrons, that means it's stable and the electrons like to stay where they're at. But look at this little guy here, see? He's all by himself. He's lonely, right? This is a copper atom. Here's a gold atom. See how it's got an electron out on the outside there?
We did this last year, and we did an experiment with a battery and stuff. And we made
So you know about this.
And then we did this.
Yeah. If the element has a free electron, like copper or gold, that means that they like to jump from one atom to the next. Check this out. You guys see that? It's jumping from one to the next. That's electricity when the atoms will flow, okay? And if we take a quick peek at the periodic table of elements, we can see where's copper? There it is. Copper, silver, gold, those are all conductors here. So depending on where it is in the periodic table determines whether it's a conductor. Let's see here. Over here is silicon. Some of these are more stable. They don't conduct. So anyway, I'm not a chemist. I don't do chemistry, but that's what they tell me anyway. The ones that are stacked up and down.
You should be a chemist.
Well, I'm a computer guy. Alright, so those are conductors. Insulators are made up of atoms that don't have that free electron that jump. They have a stable shell. Their shells are full of electrons and they don't like to move from one to the next. Examples of these might be glass or wood or plastic. Okay, so every electrical cable you have here, I've got electric cable, like here's the power cord to my laptop. It's covered in plastic. Do you know why?
Because
The copper doesn't break inside.
There's copper inside, and we don't want the electrons to jump into our fingers, do we? We want the electrons to get into the computer and give the computer
so they
electricity.
go like wow 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 wow.
Yeah, all right, thank you. Now, so electricity, where does it come from? The wall outlet?
Nope. Coal, and a solar panel.
Coal or solar panels?
Well,
All
food
right.
comes from the grocery store.
Yeah. If you think electricity comes from the wall outlet, you probably think food just comes from the grocery store too.
Well, I know it doesn't, but it
You guys
does.
have an uncle that's a farmer. You know food comes from the farm.
But I do know that you can buy food from the grocery store.
All right, check it out.
Guess what? We bought bananas.
We're talking about electricity. Okay, electric power comes from
Windmills.
Oh my gosh.
what are
Generators.
generators? Yes, a generator is connected to mechanical power source, and it turns the generator and makes electricity. Okay, so that's yes, that's called the right-hand rule right there. That little thing that shows the motion. This is the motion, the field, and the induced EMF. All right, so if you've got a field going this way, then the electrons are going to flow towards you like that. Or if I go this way, and my motion goes this way, and my field goes this way, then the electrons are going to come right at you. Okay. Okay, we're back. Computer crashed for some reason while we were talking, but that's okay. So, generators make the electricity by converting mechanical energy into electrical energy. Motors are the opposite of generators. They convert electrical energy into mechanical energy. All right, so give me an example of an electrical motor, Emily. Where'd Thomas go?
Oh no. He's probably hungry.
Oh, yeah, it is getting close to lunchtime. All right, well, let's wrap this up. Give me an example of an electrical motor.
Mm.
You probably have some in your bedroom. Anything motorized in your bedroom?
The clock.
Clock is an electrical motor. Good. Takes electricity and turns it into mechanical, and the little arms move around. Yeah. Printers, hair dryers, anything that spins around. A hard drive in a computer. All of these take electricity and turn it into mechanical motion energy. Okay? We've actually built this at home.
In this nerdy
Yeah, this
science
is what I was
project,
talking
we'll
about,
build a
Dad.
simple electric motor.
You've seen this before.
For this, you'll need a piece of styrofoam,
No, I
a
haven't.
small box or block of
Well,
wood,
you've seen something like it.
a couple paper clips, a
We
battery,
did this at home.
C or AA will probably work,
I made it.
and a magnet,
A magnet, some
and
paper
some
clips,
magnet wire.
magnet
4 or 5
wire,
will work, 26 or 28 gauge.
insulation coating on it. And so then you do like this guy. He's making a coil.
Leave some extra on the ends. Carefully remove the coil from the marker, straighten.
Alright, let's see what he's doing here. I'll skip ahead. Alright, so now he's kind of wrapped it into a circle, and he's got those leads on the end, trying to get those all smoothed out and straight. Yeah.
Remove all the insulation off of one side.
Alright, so he's scraping off.
Only remove the insulation from the top.
So you want to leave half of the insulation on and half of it off. Okay. Then you form your paper clips. You make a little tray, a little holder for them. You put a magnet underneath it. You hook up some wires to a battery, and you got a motor. The reason you strip off half of it is it's like it conducts and then it doesn't conduct. So as the thing spins, it kind of pulsates at you. Alright, some terms that you need to know. This is on the test, Emily, so you better take some notes, alright? Because we're going to have a review at the end. Go ahead, you can use this paper right here to take some notes. First term is voltage. This is like pressure. Like if you think of water pressure, how the higher the pressure, the harder and faster the water comes out. Same thing with voltage. The higher the voltage, the faster, and no, well, not necessarily faster, but the more pressure to move electrons. Okay, you get a greater movement of electrons with higher voltage.
Hey, I'm not done yet.
You can review the video. Alright, current. Current is the actual amount of electricity flowing. Okay? So if there's lots and lots of electrons moving, we say there's lots of current. If it's just a trickle of electrons moving, then we say it's low current. Alright? Current is the part of electricity that's dangerous to humans, by the way. It's the current that kills you, not the voltage.
Keep going.
Resistance. See, there's a little resistor down here at the bottom of the screen. This is what opposes current flow. Okay, so voltage. If we increase voltage, we make current go up. If we increase resistance, then we make current go down. Okay, so it opposes current, and it's measured in ohms. Current's measured in amperes. Voltage is measured in volts. All right. So now we come to what's called Ohm's law. Okay, this is a basic law of electricity, and this is where voltage equals current times resistance. Okay, they're all kind of related together. Voltage equals current times resistance. The abbreviation for current in electricity is I. So a lot of times we'll just write that equation as E equals I times R. You might want to write that one down.
What?
E equals I times R. Okay. The more voltage, the more current. The more resistance, the less current. Okay, so resistance has an inverse relationship. voltage has a proportional relationship or a direct relationship. Alright, so if current is what kills. I found this story here a couple years ago. Let's see if the browser will work now. Maybe it's not going to go. No. We're going to crash things again. Okay, here it comes. It's coming in. So a couple of years ago, about this time, it was in January or so, there was a toddler that was burned by a USB cord. It was an iPod cable, okay? It was an iPod cable plugged into the computer, and this little 16-month-old girl was hospitalized with severe burns, okay? This came in on the news, and it almost killed her. It shocked her. And so everybody's freaking out. Everybody's saying, oh my gosh, those iPod charger cables are dangerous. They could potentially kill your child. And I got to thinking, well, that's 5 volts of power there. I don't know if there could be enough current in that to kill a person. 5 volts. Now, if they put it in their mouth, there would be very, very low resistance. It's possible, but it just seemed to me like something wasn't right in this story.
Can we watch it?
We don't have time to watch the video. We'll watch it again after class, but you can.
Emily. 1 second.
What?
Well, I guess Emily's leaving me now too. She's going to go have lunch, but we're going to finish this up. Go ahead. See you later. Goodbye.
No.
Anyhow, the story didn't really add up to me. I thought it just seemed kind of crazy with that small of a voltage, even with very low resistance. If we could generate enough current to actually kill someone or burn someone that badly. A few months later, it came out. They did an assessment of the problem. There's a story there. We won't spend a whole lot of time on it, but basically, well, I'm waiting on it to load here. Basically, what happened was they brought an engineer in, and they found that a lamp in the house, hooked up to 120 volts in the house, was not grounded properly. It wasn't wired properly, and when the girl had the cord in her mouth and she touched the lamp, she became a ground for it, and that was what actually shocked her. So, very dangerous situation. But luckily, she recovered. She came out of it. But all right, another term that you need to know is alternating current. Okay, what this means is the voltage is continually moving. All right, so as your generator rotates, it's creating different voltages all the time, and that's basically what happens with alternating current. This reflects the rotation of that magnetic field in the generator, and so it's going to go to 0 volts, then a positive, back to 0, and then down to a negative. So it's going to constantly do this. And if we were to hook an oscilloscope up to the power in your house, you would see a waveform like this, a sine wave, because it's a rotating generator. Alright, so AC constantly changes. I think I'll stay here. And then direct current is just like it sounds. It flows in one direction only. All of our digital electronics rely on these direct current signals. Okay, and these are waveforms. They look like they're alternating, but basically these square waves, well, this first one would be an alternating current, but we shape them into these square waves so it's on and it only flows in one direction, and then it shuts off again. And if you notice, 0's at the bottom. It never goes past 0 and goes into the other direction. All of these, there's like a 1 volt or 5 volt, but when it turns on and it turns off. And if you've been studying computers a while, that should sound familiar. Everything's a 1 or a 0 in a computer, and that's created through these direct current signals. Okay, if the power's on, it's a 1, and if the power's off, it's a 0. So that's direct current. A circuit. A circuit is required to make electricity flow. You have to have a complete circuit. You've got to have the power source, the switch. You see, when the switch closes, then the electrons can flow. And there's the load, the light, or whatever else is being powered by the electricity. When you open the switch, the circuit is open, and you can't have a flow of electricity anymore. So you need a voltage and a complete circuit for current to flow. So that's another term. Then just to review, what is electricity?
Electricity, electricity. Flip that switch and what do you get? You get a electricity, electricity.
It's the flow of electrons. One electron jumping from one atom to another. Current, I skipped over. Item 2 there, conductors and insulators. Conductors are elements that have a free electron in their outer shell. They're prone to letting electrons move easily from one atom to the next. Insulators don't have that free electron. They have shells that are full up, and the electrons don't like to leave from one atom to the next. So they help protect, keep those electrons flowing inside the conductors. They keep us from getting shocked. They keep from having short circuits or electrons going into other wires that they shouldn't be. Motors and generators. Motors convert mechanical energy into electrical energy. No, I just said that backwards. Motors convert electrical energy into mechanical energy, and generators take mechanical energy like wind or steam or water moving and turning the turbine, or coal like my son was saying, and converting it into electricity. AC/DC is not only a really awesome rock group, but AC/DC, it stands for alternating current or direct current. Alternating current changes polarity. It goes one direction, then the other, then the other, then the other, and it does this in our household. It does it 60 times a second, 60 hertz. And then direct current only flows in one direction. So when it's turned on, it'll go this way. When it's turned off, it just stops. And then it's on, it goes this way again, and then when it's off, it stops. Okay, and that's how we get our 1s and our 0s in our computer. And then finally, voltage, current, and resistance. Those are Ohm's law. Remember, voltage is the pressure. It's kind of the potential for electron flow. Current is the actual electron flow. The more electrons that are flowing, the higher the current. And the resistance is the opposition to that flow. Voltage is measured in volts. Current is measured in amps or amperes, and resistance is measured in ohms. Okay, and that equation for Ohm's law is E equals IR. E stands for voltage, I stands for current, R stands for resistance. Then finally, a circuit is what's required. You have to have a complete circuit for electricity to flow, and that's the end of my presentation.
Electricity, electricity. Flip that switch and what do you get? You get
Thanks for watching.
Electricity, electricity. Every room can now be lit with just electricity, electricity. Where do you think it all comes from? This